I know David talked a little bit about path integrals, but just to sort of remind you how a path integral is derived, I'm not going to spend a lot of time on this, but basically the static path integral that we use for thermodynamics and equilibrium properties, you have your Hamiltonian kinetic plus potential energy, right? And what you want to calculate is a partition function from which you derive all the thermodynamic properties. Normally, you might think of doing this as a sum over the Boltzmann factor of the eigenvalues, but unless you're doing a very tiny system, calculating these eigenvalues is essentially impossible. So what we tend to do is to use a trace that's performed in the coordinate basis, all right? And so you have to do this expectation value. And of course, because the kinetic and potential operators don't commute with each other, you employ the so-called Trotter theorem. So you break it up like this. You have p factors. You divide beta by 2p. And the limit that p goes to infinity, this becomes an exact factorization. All right. And between all the factors of omega, you just insert this resolution of the identity in the coordinate basis. Each of these matrix elements of this operator here, which is this decomposition in the brackets, you can evaluate analytically. It looks like this. So that's your kinetic energy term. This is what happens to the potential energy. You put it all back together, and what you get is the so-called discrete path integral expression for the partition function. And as the limit of the number of these points that you used in the Trotter expansion goes to infinity, then this becomes the exact quantum partition function, right? Now, for finite p, the way that we think about this factor up here is it's a sort of potential energy where you have a spring that couples neighboring points, xi and xi plus 1, and a potential energy. So you have this nice picture of a so-called ring polymer. All right, so here are the points on the ring polymer. They're connected by springs. They sit in some potential energy. And the trace condition means that you have to close the ring. This thing comes back on itself. And because it looks a little bit like a necklace, we sometimes call the points on the ring polymer beads. Okay? All right. Now, if you wanted to do dynamics, so if you wanted to change from doing a partition function where you have e to the minus beta h to the propagator, where you have different points on each side. So David showed an expression for something where you have two different things on each side. Well, what you do is you open the chain. That gives you an x and an x prime. So instead of closing it, you have two endpoints. And you can change the beta to an IT over h bar, and that will give you a path integral expression for your quantum propagator. All right, and you can think of this transition between beta and IT over h bar as a kind of rotation in a complex time plane. All right, so over here on the real axis, you have some, let's say, time variable, call it theta. On the real axis, it's t. On the imaginary axis, it's minus I beta h bar. And you can go back and forth and generate expressions for partition functions in quantum statistical mechanics and expressions for real-time quantum dynamics on the real axis. And this kind of rotation is called a Wick rotation. All right. Now, that doesn't mean that doing a path integral for a propagator is easy, because this factor is, it's not positive definite, so you can't sample it. Whereas for a partition function, you clearly can, because this is a positive definite object. So this is important to keep in mind. The thing is easy to do formally. Practically, it's almost impossible when you do a Wick rotation to get something you can evaluate. So that's the challenge of quantum dynamics. This is why quantum dynamics is so difficult. Okay, so let's talk about quantum time correlation functions and what they're used for. All right, so the standard quantum time correlation function is also a trace. All right, so you have a Boltzmann factor, and then you have two operators, say, that you want to correlate. And of course, one of them is at 0, and the other one you evaluate at time t using the standard Heisenberg evolution operator. So it's going to give you an AB correlation function. And if they're functions of position, which is often the case, then you can take your correlation function and you can sort of separate off all the terms, again, using this resolution of the identity. And if that's a function of x, that's a function of x. You can replace these by their eigenvalues. And so you get a product of matrix elements of either forward time propagators or backward time propagators, because you have a plus sign here, or Boltzmann operators. So a kind of nice picture of this is as follows. All right? So if you start here at x, you propagate in real time from x to this point x double prime, and it's there that you measure the operator b. Right? So you evaluate b. Then you go from x double prime to x prime. This is backward in time. And once you get there, you measure the operator a at this point x prime, and then x prime and x are connected by a Boltzmann operator. Okay? Now we know that we can get a path integral expression that we could evaluate for the Boltzmann term. These propagator terms we can't, again, because they're oscillatory, they're not positive definite. But formally, this is a nice way to look at a standard correlation function. And what are some of the things that you can get from correlation functions, all right? So these are all examples from real systems that we've done. I'm not going to talk about any real systems today, but at least they're there. So for example, you might get a transport coefficient by using Green-Kuba theory and integrating the correlation function. This is an example from fluid parahydrogen where we looked at the velocity correlation function and we got the diffusion constant from it by integrating it. Spectra, all right, so you take the Fourier transform of a correlation function and you might get, for example, an infrared spectrum. That's an example being shown here for sodium hydroxide solutions. Or you might get a rate constant. And depending on which correlation function you do, you may have to take the long time limit of it, or the long time limit of a derivative of it, or an infinite integral of it, something like that. And this is something you can plot as a function of temperature. And this is an example that we did for hydrogen diffusion in structure 2 clathrates. All right, so this is just some motivation for why you want to study correlation functions, why they're important. Okay. Now, correlation functions, as I said, they're extremely difficult to calculate in quantum statistical mechanics. There are some kind of handy approximations that have become very popular. So remember, this is the path integral expression for the partition function. Everything is in this imaginary time or statistical mechanical formulation. And so one of the common approximations that goes all the way back to 1983 is this so-called centroid molecular dynamics. So what you do is you take an average over this distribution here of a quantity that's called the centroid. In other words, you take the average of all the points on your ring polymer. You set it equal to some value xc. And if you multiply that by the derivative of your potential, then you get a so-called force on the centroid. And if you plug into sort of classical equations of motion for this centroid, you can evolve things in time. And this so-called centroid dynamics is a kind of a way of sort of a little bit of an ad hoc approximation for getting time correlation functions. Notice there's no phase behavior in here. So there's nothing, there are no actual propagators in here, all right? So it is a cheap and easy thing to do, but you lose a little bit of the physics. Where did the propagators actually go? Okay, ring-polymer dynamic, centroid dynamics has kind of been replaced of late by the so-called ring-polymer molecular dynamics scheme. And in ring-polymer dynamics, you pretend like this thing up here in the exponential is a potential energy, and you evolve all the beads by turning this into a Hamiltonian. You just put a kinetic energy term, and you move the beads around according to equations of motion where the force comes from the derivative of this. Okay? Oh, this is called ring-polymer molecular dynamics. And again, there's no propagator in here, all right? So you get some dynamical information, but again, it's a little hard to see where the physics comes from because propagators are gone. All right, now there was some very nice work from Stuart Althorp in recent years where they derived a kind of formally exact complex dynamics that they call Matsubara dynamics, and you can show in fairly complicated ways where these two approximation schemes come from. And it doesn't mean that they're easy to correct, but it at least gives you a little bit of insight. Okay, so you can ask the question then, why do we need another scheme for quantum time correlation functions? So we have these imaginary methods, centroid molecular dynamics, ring-polymer molecular dynamics, so on and so forth. Why not just stop here and say we're done? Well, So these methods are actually okay sometimes for linear operators, so things that are linear functions of position like dipole moments. They lose accuracy for nonlinear operators, and these are operators that, yeah, if you do rate theory, you usually have to calculate. All right? It's hard to find systematic improvements of these methods. So if you can think of another approach in which you actually start with the exact expression for the thermal quantum time correlation function, you might get some new insights, and you might get a pathway into new strategies for calculating quantum time correlation functions where you can really see what you're doing. Okay, so that's what I'm going to try to convince you of today, that there is a new way to look at these things. You have something that may be systematically improvable up to a desired accuracy, so on and so forth. All right. Now, the imaginary time methods that we talked about, centroid and ring-polymer dynamics, go after a different kind of correlation function. All right, so there's something called the Kuba transform correlation function, in which you sort of take all the points along that Wick rotation pathway between the real and the imaginary times, and you integrate over that, and you divide by beta. So you're sort of averaging over all these times, and you take your standard correlation function, and you do that. And what you can show is that if you go into Fourier space, you Fourier transform these things, the Kuba transform correlation function is related to the standard one, the one you're usually interested in, by this little frequency-dependent factor here. Okay? So it's easy to recover the standard correlation function if you can calculate that. All right? So the way that, if you're doing centroid MD, then the actual approximation you make is you evaluate your A and your B along the centroid, and that gives you the Kuba transform correlation function. And with ring-polymer MD, you take an average of your operator over all the beads of the ring-polymer, and you do this correlation function. All right. There's actually another correlation function of interest, which is called the symmetric or symmetrized correlation function. And in this one, what you do is you take the standard correlation function, but you evaluate it at a kind of complex time. So in other words, you take the operator A at 0, you take the operator B, but you're evolving it in this Heisenberg-like picture, but where the time is a complex parameter, t minus I beta h bar over 2. This is actually kind of the midpoint of that integration for the Kuba transform correlation function. And again, there's a fairly simple way to connect this correlation function to the standard one. All right, you have to multiply by this really terrible factor of e to the beta h bar over 2, which is not something you ever want to deal with because, for high frequency, this gets really big. So you better make sure that your errors in the GAB are very small there, because this will just amplify them. But there is a way to get back to your standard correlation function. You can also connect it to Kuba through a simple formula like this as well. Okay. Now, again, if your operators are functions of position, then you can separate off the terms like this. So you have matrix elements of these complex time propagators between x and x prime. And a nice way to visualize this is as follows. So you start at x. You measure the operator A there. And then you move from x to x prime forward in complex time. So you go here to here. This is in this complex time evolution. There you measure the operator B. And then you come back backwards in complex time to your point x, all right, with the complex conjugate of the complex time variable. Okay. Now, an interesting thing about this symmetrized correlation function is that you can combine these two factors here and here, and you see that you get something that's positive definite. All right? Yeah, it's only positive definite in the two endpoints, x and x prime. So that doesn't help you very much, but this is a result we're going to need a little bit later. Okay, so let's just derive the path integral for this very quickly. There's your Hamiltonian. This is your complex time parameter and its modulus. So if you insert your Trotter expansion, then what you basically get, because you have two of these factors, so you're going to get a P bead chain for the first propagator, a p bead chain for the second one, so I get a total of 2 p beads. But because I go from x to x prime and then come back to x, it's also a ring polymer. Okay, so after you do all the math, you find that the correlation function on this 2p bead ring polymer has a positive definite density and a phase. And both of these involve all the points of the ring polymer. Right? So everything is evaluated on the ring polymer. The density looks a little bit like what we had before, except there's some factors of 2. Otherwise, there's a kinetic term, potential term, and of course, this complex time parameter comes in. So that involves both beta and t. And then you have a phase, which is actually the difference between the forward and the backward paths. All right? So this is the kinetic energy of the forward path that goes from 1 to p, then from p plus 1 to 2p, that's the backward path in complex time. And you evaluate the potential also along the forward and the backward paths. You take the difference. All right? So if your system is not very quantum, and the phase doesn't matter very much, you would expect these terms to be rather small. Although each one individually can be quite big. So it's the small difference of large numbers problem. Okay. And of course, you have the trace condition. This is why it's a ring polymer. So this is what it looks like. There's your ring polymer. These are the beads for the forward path. These are the beads for the backward path. And you're evaluating everything on this. But now let's imagine doing a transformation of this path integral. And the kind of transformation we're going to use is motivated by work that goes on in the semi-classical community that assumes that the difference between the points on the forward path and the points on the backward path are rather small. All right? So what we're going to do is we're going to take the average of points on the forward and backward paths, we'll call that R, and the difference of points on the forward and backward path, and we'll call that S. All right? Okay. Now, you can integrate over the S's, and you'll get some very complex potential that basically couples all the beads, but it'll be a function only of R. And if you look at what the R chain looks like, so if you reformulate your chain in these sum variables, it's an open chain. Okay, so you don't get there's no trace condition anymore. You don't have endpoint matching. So you're doing an open chain now, all right? You can invert the transformation very easily like this. So it's a fairly simple transformation, but you get a lot of very interesting results from it. So now we've reduced the number of points from 2p to back to p plus, it's p plus 1 in this case. So I have an open chain with p plus 1 beads, all right? Okay. Now what I want to do is to prove a little theorem for you that shows that with these open chains, so if I'm willing to sample open chains, there is a formally exact distribution, positive definite, on the open chain that gives me exact quantum time correlation functions, formally. All right, so, and it's the symmetrized correlation function. So this is what the integral over the difference variables looks like. I have some positive definite distribution again, and I have some phase factor. The distribution looks like this. The phase looks like this. This is this path difference again, all right? And what I want to do is to perform the integration over S formally. Okay, so I can't do it analytically. But formally, I can imagine integrating out all these S variables. When I do that, I'm going to get some function only of R. So I'll call that result I of R. Okay. Now, what I'm going to show is that this I of R is a positive definite object. All right. Now, remember, the original expression that we had was an integral over the two endpoints, x and x prime, with this positive definite object here as a function of just the endpoints. And in our new notation, x is x1 or r1, x prime is this xp plus 1 or rp plus 1. All right. This is positive definite. And once I've done the formal integration over S, this is what I'm left with, okay? I'm left with a factor that looks like this as a function of R, and I'm calling this factor U of R, T, and beta. And then I'm left with this I, all right? This thing where I integrated out the s's formally. So that's that I integral, all right? But now, because this is positive definite, and the whole thing has to be positive definite, apart from the a and the b, the only possibility is that this integral that we did is also positive definite. In other words, I can write this I as a kind of Boltzmann factor where this V tilde is real. It's a real potential, all right? It exists formally. And that means that if I go to this open chain as a function of the R's, I have an exact distribution that I can sample for calculating the symmetrized time correlation function, all right? So I've gotten rid of all the phase factors just by integrating out these path difference variables. And so now I have something that formally gives me exact quantum dynamics. All right? Okay. So first of all, just here's a very interesting and elegant way of looking of what these open chains kind of mean for rate theories. All right? So let's just remind ourselves what you're doing when you're calculating a rate, all right? So the rate, as I indicated earlier, is a long time limit of one of these symmetrized correlation functions. And the correlation function you have to calculate is indeed a nonlinear function of your coordinates. So you've got what's called the side function, which is basically a step function that puts your system initially in the reactant well, and then you look at a flux operator, all right, that looks like this, and of course it involves momenta, and a delta function, all right, that would put you at the transition state. So Q double dagger is the location of your transition state. And within the ring-polymer molecular dynamics scheme that I showed earlier, the way you'd calculate this is you would first calculate a probability to find your system at the transition state in the first place, and then once you had that, you would take your ring polymer and you would launch trajectories starting with the centroid at the transition state. You get your transmission coefficient by counting the number of times that you go to the product state as a function of t, and then you put that all together. And in the long time limit, that gives you your rate constant. Now, in this open chain formulation, something really nice emerges. I think it's really elegant. Let's, instead of using the flux side correlation function, let's use the side-side correlation function. All right, now this is one where instead of looking for a plateau, you would look for the linear regime like you do for a diffusion constant, and then you would take the derivative of that in the long time limit, so you're looking for the slope of it, and then that would be your rate constant. So the correlation function that you're looking at is a correlation function between two sides, one for the reactant side, and the other for the product side, okay? All right, so in our open chain formulation, this is the correlation function we'd have to calculate. It's now just an integral over the open chains. This is our e to the minus beta v tilde, or this I thing, and then the U potential. And so this is what you're looking for. You're looking for an open chain that starts in the reactant well, and where the endpoint goes to the product well at the end, all right? So that would be a productive or reactive contribution to your side-side correlation function. Now, what's really interesting is that, of course, for short times, what do we expect? Well, we expect that tunneling is kind of going to dominate. That's a fast process, all right? And at short time, so at time small, you can take the chain to have very few beads on it. So you have a short open chain, all right? And a short open chain is not going to be able to go over the barrier very easily, so most of these chains are going to sort of tunnel through. As you go to long time, you expect more activated processes. Of course, for longer times, the chain has to get longer, and so these chains are more likely to cross over the barrier. All right, so this gives you a really pretty picture in which you can sort of see the short time emerging as these tunneling paths, and the long time looking like this. All right. Now, how can we approximate this thing? So I said formally, I have this Boltzmann, this potential. It couples all the beads of my open chain, but I can't, it's only formally exact. So how can I begin to approximate this thing? Oh, so one of the ways you could do it is to use a second order expansion, all right? So unlike semi-classical methods, which stop at linear order, we're going to go to second order, all right? So what you do is you'd say, well, I assume that these path differences are small. And so I'll take a potential term that looks like this. This is what comes into the potential. And we'll just expand it out to second order, all right? Now, interesting, in the positive definite Boltzmann distribution that you have, the linear terms cancel out. And so you get something that just involves the even powers of S. And if you stop at second order, it looks like that. In the phase part, now we're going to integrate out, the even terms cancel, and you just get the odd powers of S. So if you stop at linear order, then you would have something that looks like this. So now I can do the integral that I said I can only do formally. Now I can do it exactly analytically. I have it's the second order. I have a matrix. I have a vector. So it's just a simple Gaussian integral. And so my approximation for this Boltzmann factor, this I integral, is the standard form of a Gaussian integral. It just looks like this. Okay? And you can see that's a fairly complicated function of R. And it couples all the beads. So it's no longer just summing over potential terms of one bead at a time. This is highly coupled, all right? Okay, so what you get at the end of the day is something that has all these different terms in it. You have to evaluate this. And this W potential has a kinetic term, a potential term, and then this part, this V tilde, that couples all of the beads. Comes from this Gaussian integral, where the vector looks like that and the matrix looks like this. So it's a fairly nasty thing, but it's something that you can actually evaluate. Okay, this can be evaluated using path integral Monte Carlo or molecular dynamics. So let's see how it does. Right, so I'm going to show you a couple of simple one-dimensional examples of potentials where you can calculate the correlation function exactly, because it's 1D. And in a way, this is actually a little bit more difficult in doing things in condensed phases because there's no decoherence, all right? There's no quantum decoherence. So basically, these things just oscillate forever. They never really die out. So we'll do the harmonic oscillator. We'll do a weakly perturbed harmonic oscillator. We'll do an anharmonic oscillator and a double well potential. And notice that, yeah, David.
That last remark was if you're doing molecular dynamics. Or if you're doing Monte Carlo, it wouldn't matter.
No, it doesn't matter. These are still one-dimensional examples. The correlation function is what it is, whether you evaluate it with MD or Monte Carlo.
But you were saying in condensed phase, these are difficult to evaluate.
No, what I'm saying is that in condensed phases, correlation functions tend to just decay to zero, right? So you get because of
so you have to go to longer time with.
Yeah, you don't have to go very far out in time before you see it decay. These won't. Because there's no other degrees of freedom, just the one that you've got here. These are one-dimensional examples. Okay, so because I expanded to second order, of course, my scheme is only exact for harmonic potentials. All right, so it won't be exact for these, but we can see how we do. All right, so we're going to be comparing to RPMD, ring-polymer MD, and we're going to be comparing also to a semi-classical initial value representation using thermal-Gaussians. If you don't know what that is, don't worry about it too much. I think the real comparison here is with RPMD. Okay, so this is the harmonic oscillator. These we're doing with path integral MD, all right? Now that's a bit of a pain because now I need third derivatives of the potential. For these 1D examples, there's no problem, but in real condensed phase systems, you wouldn't want to do this, all right? But it does allow us to go out to fairly long times, all right? So you can see that, for the harmonic oscillator, everybody is working pretty well. You don't see the differences between the exact and the RPMD and the IVR, the semi-classical one, and our open chain, right? That's for the x correlation function. But now let's look at the x squared. That's a nonlinear correlation function, all right? And you can see that now the RPMD, for example, is not quite getting, the right It's not going down all the way. Right? So it has the right frequency, but it's missing this region a bit compared to the exact, which is underneath the green. The open chain is doing okay. There are some errors as you go to longer time. The chains get longer. It gets harder to sample, right? Especially because you need the end-to-end point. You're correlating the endpoints of an open chain. That's not so easy, all right? But within error bars, we seem to match the exact results. That's it at high temperature. This is low temperature, all right? So at low temperature, again, XX is fine. A nonlinear correlation function is a bit harder. It's really small, so your errors are big. Everything is sort of within error bars. The RPMD kind of gets the right frequency, but it's way up here, right? So it's way off in this one. Let's go to the weakly perturbed oscillator, all right? So again, if you're at high temperature.
Sorry, Mark. The RPMD, is that a fixed number of beads?
It's a fixed number of beads, yeah. That one you don't have to increase the number of beads because the time is the parameter of your molecular dynamics. So you just run a path integral MD trajectory and you pretend like the dynamics that you use for sampling is giving you quantum dynamics. So you just do a ring polymer and that's it. All right. Whereas here, when you do trying to do actual correlation functions, as time gets bigger, you need more and more beads. Right? Okay. We have to put in more and more beads because you want tau over p to be constant. Right? So high temperature, all right, everyone's doing pretty well. For x squared, the nonlinear correlation function, there are some small differences that come in for the RPMD, the semi-classical, and the open chain generally do pretty well. All right, now we go to low temperature. All right, now things start to get kind of interesting. So the open chain is kind of not doing so well. Okay, you get the right frequency, and you can see the RPMD is sort of missing the frequency. It's getting out of phase with the exact result. So it was the semi-classical one. Okay, we're going to see what the source of this error is in a moment. All right, but something to keep in mind, something is not quite right there. So we'll get back to that. So the quartic oscillator, the anharmonic case, that's high temperature. Okay, that's the exact result. Nobody really gets it right because it's a quartic oscillator. It's really hard. All right, but so you can see that the RPMD and the open chain do pretty well. The semi-classical one, not so well. For x squared, nonlinear oscillator, okay, again, nobody's getting the exact result too well. The open chain is actually doing the best, at least until you get to here, and then they all sort of poop out, and they don't do too well. Is the black? Yeah, the black is the exact result. Yep. As you can see there. And now you get to the low temperature case, and again, nobody's doing all that well. So RPMD gets out of phase. So does the open chain one. We'll come back to that point. And the semi-classical just. All right. So that's a tough one. This quartic oscillator is not so easy. And then there's a double well. All right. So now we have a possibility of tunneling depending on the temperature. That's high temperature. Again, XX, they kind of all do about the same. X squared, again, the open chain is doing probably the best for this one. It's known that, if you do RPMD, it's hard to get tunneling right. So at low temperature, now we're starting to see that the open chain is having a little bit of a problem, all right? So does the RPMD, but it does a little bit better. Here it's above, and for X squared, it's a little bit below, all right? So where are we having problems with, especially some of these low temperature regimes that we're looking at? Well, it turns out the normalization is a little tricky for these correlation functions, right? So you imagine that, you've changed now the potential for this open chain, especially when you're doing things at this second order, all right? So that's my V tilde. And so the thing I should be normalizing by is, so that's when I do the average, this is kind of like the partition function that I'm getting as my normalization. But I should be using the actual one. right, which I don't know. All right? So in order to correct the results, I need to multiply by a scaling factor that it depends on time. So it's the ratio of these two partition functions. We'll call it R. And this is not an easy thing to get. So I'm going to show you results first for a simple kind of empirical way of getting it, where you just take something and you average it, and you think that average should sort of give you the average of the partition functions, assuming that the observable isn't changing very much. So for the linear ones, we'll use this, and for the nonlinear one, we'll use this. And let's just see how these kind of empirical scaling factors do. All right, so let's go to the weakly perturbed oscillator. All right, so at beta equals 8, that's where we had the real problem. That's for x, the linear correlation function, and you can see that it kind of corrects it rather nicely. And the problematic case, the nonlinear correlation function, that's the old result, the blue, and the red is the corrected result, and now it's kind of getting back on the exact result nicely. And for the anharmonic oscillator, this is the old result. Again, way off, but if you correct it with the right scaling factor, now you're much closer to the exact result. So we had to realize that this normalization is not so easy in this case.
Is it true that that normalization is independent of the operators you're looking at?
Not really. That's an approximation. It really isn't, all right? And that's why I'm coming to this. How should we really do this? Now, what we really should be doing is trying to get the partition function ratio. But a partition function ratio is a kind of free energy, all right? So what we actually want to get is a free energy, in this case, for going from a closed chain to an open chain, or open chain to a closed chain. So I've kind of represented it pictorially like this. All right, so at t equals 0, your chain is closed. But then when you go to finite t, of course, you have this open chain. You have to, so you have to transform from this t equals 0 result to the one at time t. So think of that as a free energy to open the chain, or you can go backwards and get minus the free energy change for closing it. And okay, these are not easy integrals to do. There are different ways you can do them. One possibility, which we're actually going to try, is this nice method by Lin, where you do a displaced path integral. You do everything with closed chains, and then you do a perturbation approach to it. Okay. What about getting second derivatives? All right, so you saw that there's a Hessian, that when you do the second order expansion, you have to calculate a second derivative. You really want to do this analytically? Well, all right, you can ask the question, do you need to do that? So, or is it maybe enough to get these derivatives numerically? So one example would be to take the potential and do this kind of second center difference formula. Or you can take the derivative, that's the first derivative is not so bad, and you can do a finite difference of that, and you can compare them to the analytical derivatives. Because this was work actually done by Scott Habershon around the same time we were doing this. And so what's the bottom line? If you're at high temperature, you sort of get, at low temperature, the analytical derivatives actually don't do as well as the fits. At high temperature, it kind of goes the other way around, and I don't entirely understand that. But that's what these experiments are showing. Same thing for the nonlinear operator, and that's true for the weakly perturbed or the anharmonic case. So that's something we have to kind of, if we're going to go with this second order expansion, I'd like to try to understand that a little bit better. Okay, now it comes to the Monte Carlo part. All right, so this is work from Alan. And so we have these endpoints, and we have to sample the endpoints of an open chain. And if you've ever done anything with polymers, you know this is extremely difficult to do. So I've spoken here at the IPAM many times about our temperature-accelerated molecular dynamics approach as a way to enhance the sampling of something. And so the idea is that, let's suppose I have some collective variables. They're functions of my position, so I'll call them Q alpha of R. And there's a dynamics that you can use to enhance the sampling of this set of collective variables. This is called adiabatic free energy dynamics or temperature accelerated molecular dynamics. Basically what you do is you have a harmonic coupling between the collective variables and some external variables that will characterize a marginal distribution. You evaluate them or you evolve them at high temperature. The physical variables are evolved at time t. This is the potential that I have. And then you can easily recover the free energy by just taking a histogram of these S's as you generate this dynamics. It's really quite simple. All right. Well, but I don't want to do molecular dynamics necessarily. So what we're going to do is we're going to switch to something called temperature accelerated Monte Carlo. That's something that was derived by Giovanni Ceccotti after this temperature accelerated MD came out. And what you do in this case is you replace this MD for the physical variables by a Monte Carlo algorithm. But you keep the dynamics of this external set of variables I am using to characterize my free energy because it's quite simple. So what you end up doing in this case is you do sort of a half-step evolution of your external variables, and then you do MC, Monte Carlo, on your physical variables, and you use that MC sampling, the Monte Carlo sampling, to get an average of this force term here, all right? And then you can complete the MD evolution of these. Sorry about the change of notation. That's mine, and that's the notation of the paper. But the theta is the Q, and the Z is the S. I'm sure you figured that out. So that's how temperature accelerated Monte Carlo works. What Monte Carlo are we going to use? Well, we're just going to use David's staging Monte Carlo scheme, from 1984, but we've adapted it for open chains. And there's a number of ways you can do that, and we're still tweaking it. So I'll only have some preliminary results to show you at this point, but these are results that Alan generated for our anharmonic oscillator, the quartic oscillator, at high and low temperature. Okay, and what do you see? Well, you can see that, at high temperature, the green are what you get from doing MD for a certain length of time and then trying to get the same number of force evaluations for the MC, and basically you do converge a bit faster when you use this temperature accelerated approach. The collective variable here, by the way, is the end-to-end distance, all right? So we can really sample the fluctuations of this open chain and move the endpoints around. Low temperature, okay, so remember, low temperature is harder to converge, and so if you just do MD for a certain length of time, it takes a long time to converge it, but the temperature accelerated MC is actually doing much better. Now, we haven't taken these out to long time yet, and the reason is that as you go to longer and longer time, the acceptance goes way down. And we're trying to figure out why the acceptance goes way down or how we can maybe improve the algorithm to get that acceptance up. So, that's why we're stopping at times much shorter than we were able to do by molecular dynamics. Okay, let's see. This open chain thing should not suffer from what is called the curvature problem. This is something that was identified by Dominique Marx some years ago, where they said, look, if I'm doing something with centroids, anything that involves centroids, like centroid MD or rate theories where I have to put a centroid somewhere, let's take an example of a radial potential, all right? So if I'm at high temperature and the chain is short, and kind of, well localized along, this is my radial surface, so localized here, then the centroid is a good approximation for some point on that radial potential. But if I'm at a low temperature and the chain becomes quite delocalized, and you have something like this, the centroid is not here. It's actually somewhere here inside. And so the centroid starts to get an unphysical position location on my potential surface. And that screws up the calculation of observables. All right, so this is called the curvature problem. And since we're not using centroids, we're actually trying to get, at least approximately exact dynamics, we shouldn't suffer from it. All right, so let's take, a radial potential. This is in 3 dimensions. And if I set, the center to 0, I can do things analytically. And so that's my OPSCF result, my open chain result. Now, if I make the center not 0, then of course I no longer have 3 separate oscillators. So I don't have the exact result for it because it's not a harmonic problem anymore. But the result that we get is this yellow one. It looks reasonable in the sense that when you move the center, all right, now you have something that's moving around a spherical surface. And so, of course, you expect, the frequency changes and you get a shift in the amplitude as well. So the results kind of go in the right direction. And just for fun, we did a molecule. And I can show you what these open chains look like, let's see, at different time points, all right? So this is what the open chain is doing for this OH molecule at 10 femtoseconds. Okay, so the sampling looks kind of weird, but it's also kind of cool. And of course, as you go to longer time, the chains get longer. And so that's the kind of space that you're sampling, all right, for this, again, for this radial potential.
What's the relation between the orange? Oh, I see those.
One is O and one is H. So you have two open chains now, right?
And the H is much more dynamic.
Yes, and it's much more, yeah, like it's more quantum, right? So the chain is longer. Okay, all right. Other schemes. So if you want to do better and a little, something that's maybe more exact than a second order expansion, you can imagine doing this. Right? So you can imagine you have to do this integral to get R, right? This is the integral over the difference variables. So let's instead do a histogram of my phase, all right, this phase function. So this is the thing I'm going to sample. Now I can sample the S's, get a histogram of the phase at a fixed R, and then I just have to do this Fourier integral, all right, this integral over this one-dimensional variable, this chi bar, all right? I can do that by Fourier transform techniques. Obviously, if this histogram isn't very, very accurate, this will just amplify the noise. But, so Alan did this really nice movie of our anharmonic oscillator again, where he did the histogram of the phase and let it evolve. All right, so this is with your temperature accelerated Monte Carlo over time at beta x1, so that's the higher temperature case. And you can see that this thing eventually converges to something that looks like a nice Gaussian. So if this proves to be true for many time points, we may just be able to fit this and then do the integral analytically, all right? And that will take away some of the noise. So that's something we have to test. Another thing that we've kind of been playing around with, I don't know where this is going to go, but there's complex Langevin equations that are used in field theories and polymer dynamics and stuff like that. And we may be able to do an integral like this with a complex Langevin equation. I don't know. That's kind of been a little bit of a hobby project. So we'll see. Okay, very quickly, I'm just about to finish. We've started to do excited states, all right? So now you have several surfaces, and you have some coupling between them, and you're looking at processes, where you have dynamics on some combination of these surfaces, all right? Well, all right, and so two quantities that are going to be important in this derivation are the average and the difference of the two potential surfaces. And usually what you're looking for now is a kind of rate that comes from a correlation function like this. It's, you start with the symmetrized one, and the rate that you want for transfer from, let's say, a donor to an acceptor site is, for this particular case, you have to integrate. So it's from the Fermi's golden rule, and it's like the zero frequency integral that we had before. So you have to do that integral, right? Now, if I do the second order expansion like we did before, then everything looks kind of the same, except that now I get complex terms involving this difference potential. So now my correlation function is no longer positive definite. So that's a little bit of a downside when you want to do excited state processes. You have these terms here, and you have now a phase that you have to worry about. Okay. What we found, though, is that we can kind of weight the averages by the phases, and as long as we don't have to go too far out in time, we're okay. So we applied this to the spin boson model, which is completely harmonic, all right? But everything is being treated quantum mechanically here. So I actually have now n path integrals for the beads and my two surfaces. And we did this with an ohmic spectral density function, so we chose frequencies from this exponential, and we did 19 Bath modes, all right? So these are the correlation functions that we get. This is my last slide, by the way, so I'm basically done. And what we found is that if you just do the raw data, all right, then you get some errors, especially as you go out to the tails of your correlation function. So that's the log. But at least you're good for orders of magnitude. So down to 20 to 10 to the minus 20 or so, 10 to the minus 20. Then you start to get some noise. But if you smooth it with, in this case, a Whittaker Ellior smoothing function, then a lot of that goes away. All right, so these are two different temperatures. That's high and that's low temperature. That's the correlation function. That's the exact result for that coupling frequency equal to 0. But then we got rates, actually, for different values of this omega. So that's kind of the exact result from Fermi's golden rule. The raw OPSC, open chain is the red. But if you smooth, again, this nasty stuff goes away, and you can match very nicely, which you should be able to because it's a harmonic problem at the end of the day. All right, so finish up with just some outlooks. So the one-dimensional examples are difficult. I think it'll be interesting if to go to the condensed phase where you expect some degree of decoherence, and you have to ask the question, can we survive long enough to see the decay of the correlation function and get accurately enough that that exponential factor of frequency we have to apply doesn't get too big. And survival here means, going out to times that are long compared to beta h bar, but how long? What else can we prove about this potential that we know exists? We can prove it exists, but we don't know what it is. So what else can we prove about it that may help us model it in some way that's better than just a second order expansion? So what kinds of things can I prove about that? Exact properties, limits, things of this nature, right? Could I do some kind of variational optimization that may bring in a machine learning sort of approach, right? Using maybe something like Gibbs-Bogoliubov, because after all, it is a potential of mean force surface. It's like a free energy. Given this formally exact approach, can it help me understand centroid and RPMD in a different way? I don't know. Some more math to do. Extensions to identical particles or multi-time correlation functions. What does that look like? So if we start to have exchange statistics, what do these things look like? If I have multi-time correlation functions for doing nonlinear spectroscopies, what do they look like? All right. So there's more math to do there. And is there a way to go away from the symmetrized correlation function and maybe extend this approach to either Kuba transform or some variant of the Kuba transform correlation function that may be a bit nicer to work with than the symmetrized one, which although it has nice properties, it's hard to recover the standard correlation function. So I'm going to stop here and see if are there any questions. Thank you.